Since today is going to be the day I finish presenting Stephen Hawking, his views for you, I'm going to deal with right now in this lecture the huge problem that Stephen Hawking, as an atheistic physicist, is going to face, he's facing, and which partially explains his book, The Grand Design. First of all, in order to sort of get the soil loosened, I thought I'd put some, as I call them, the cosmic quotes from Chesterton, which focus on and express so much of what we run into when we consider these topics. Number one, you should not look a gift universe in the mouth. Number two, if the cosmos is unreal, there is nothing to think about. And finally, from his book, Heretics, speaking about himself and those who engage in similar activities, we shall be left defending not only the incredible virtues and sanities of human life, but something more incredible still, this huge, impossible universe which stares us in the face. And when we look at this and think about this, we run into the fact of a new discovery that has been given to us by physicists, and that is what is called the Anthropic principle. All right, the Anthropic principle. And of course, anthropos means man, okay? So what is this anthropic principle that science is having to deal with in our own time? Well, by the middle of the 20th century, physicists had come to realize that the familiar world in which we live and have our physical being constitutes a highly improbable formation, a contingency about as unlikely as randomly picking a pre-marked grain of sand in the Sahara. All right, I'm quoting this description of the anthropic principle. I'm quoting from a man who I came to know, a former professor at MIT, named Wolfgang Smith, who was describing this anthropic principle. What is it? What are the implications? And I'll just read that again, that first part. Physicists in the middle of the 20th century had come to realize that the familiar world, emphasis on familiar, in which we live and have our physical being, meaning man, meaning us all, we live in this world, we have our physical being in this world. This world, according to the claims and the knowledge grasped by modern physics constitutes a highly improbable formation. Emphasis on improbable formation. A contingency. And why does he use that word, contingency? Because it didn't need to be the case, but is. All right? It didn't need to be the case, but is. About as unlikely this world as it is formed, exactly as it is formed, is about as unlikely as randomly picking a pre-marked grain of sand in the Sahara. Professor Smith continues. I mean, think about that. Pre-marked grain of sand in the Sahara. In other words, practically impossible. And yet, it is. All right? And yet, it exists in this way. By then, I continue, by then, meaning the middle of the 20th century, and we're really focused, the anthropic principle really came to light in the year 1974. Okay? It was first spoken about in 1974. By then, it was clearly understood that a handful of fundamental numerical constants, such as the ratios of the nuclear, electric, and gravitational forces, determine what is physically possible and what is not. One came to recognize that the atomic molecular structures upon which life depends demand an immensely delicate balance or near balance of opposing forces, which in turn demands that the constants of nature assume the values they are found to have with almost zero margin of tolerance. What does that mean? Just one question. What does that mean? Yes. It has to be as it is, right? It has to be as it is. If it wasn't, what would not be? Man, right? Man. The existence of man would be impossible. And if man, the existence of man were impossible, then what couldn't happen? Then the universe or nature could not know itself, right? Nothing could know nature, but nature would be blind to itself, all right? But everything happened just as it had to for man to exist. And he gives an example here, Professor Smith. He gives an example, and the example is this. He says, an analogy. He says, it is as if the distance between the centers of the earth and the moon had to be what it is to within the thickness of a hair. Or else one cannot, dealing with this fact, the exactitude of creation. Let's just write that down. What explains the exactitude of creation? Exactitude. We can't help asking. We can't help asking, okay, well, just that, why can't we just say, well, that's the way it is? All right. Well, we'll go 1 second, go to St. Thomas. I probably told you this before, but he has an example, okay? The farmer goes into his house, all right, and he sees that his whole room, the whole house is covered with manure. All right, he walks into his house, there's manure every place. Okay, all over. What does he say? All right? This good farmer. What does he say? Does he say manure? Or more likely, what does he say? He says, who did it? Who did it? Right? Who did it? Who caused it all? Obviously, someone did it. Obviously, there was some rational activity here. Who did it? Well, we're naturally led to the question of who did it. Okay? And as we go through these examples of what are also called anthropic coincidences, all right? Because we don't want to go too far. We're anthropic coincidences, they're also called, okay? All right, we don't want to go too far. There's coincidences. As we go through them, we ask the question, who did it? We can't help but asking the question, who did it? What are some of these coincidences? Okay, let's do this one first. Okay. The charge of an electron and of a proton. Okay. I'll give you a reading from an example. The charge of an electron and of a proton, as determined experimentally, are found to be equal and opposite. All right, the charge of an electron and of a proton are determined experimentally. They are found to be equal and opposite. Their ratio is consequently -1. What would happen if this ratio were ever so slightly changed? Given the atomic constitution of matter, one finds that an explosion would take place. The opposite charges of protons and electrons would no longer cancel out, implying that the material object would become electrically charged, positively or negatively, depending on which of the two elementary charges dominates. Not only would objects repel each other, but each would repel itself internally. which is to say, they would explode. Okay, how much is this? This 1 billion? It's 1 billion. 1 in 1 billion. Okay, can I erase these Chesterton quotes, these cosmic quotes? Just 1 in 1 billion. Okay, 1 in 1 billion. We'll make the little, okay, here we go. Okay. 1, oh, you can't see that, can you? Just 1 in 1 billion. Where'd that, oh, here it is. 1 in 1 billion. 1 billionth, 1/1 billionth. That's 1 billionth, right? Okay. Million, thousand, yeah, 1 billionth. Okay, here we go. Okay. A change in the ratio -1. Okay, we're talking about the ratio, the canceling out of the charge of electron and proton. A change in the ratio -1 by as little as 1 in 1 billionth, 1/1 billion, would suffice to blow our world apart in a split second. Whoa. That's what a coincidence that is. Okay, what a coincidence. Let's get some more coincidences. Just happens to be the case. Nothing to see here. Okay, what about at the cosmic level? What about at the cosmic level? And guess who I'm quoting here? All right, not Professor Smith, who couldn't stand Stephen Hawking, but guess who? Stephen Hawking himself. Okay, who's talking about the anthropic principle and what it entails. By the way, the chapter that this comes from is called The Apparent Miracle. Okay, lest you get too excited with the idea of miracle, he's qualifying it the apparent miracle. Okay, there you go. Okay, so now he's going to speak at the planetary level. What about this anthropic coincidence at the planetary level, the cosmic level? Okay, this is what he says. This first example. Any solar system with multiple suns would never allow life to develop. In fact, a planet could experience a pleasant temperature while orbiting multiple stars, at least for a while. But uniform heating over long periods of time, a situation that seems necessary for life, would be unlikely. Okay, so I'll repeat that. All right, so could life exist on a planet that was orbiting two suns? He says, well, you might have a pleasant temperature for a while, but uniform heating over long periods of time, which is necessary for life, would be unlikely. In each of these orbits, there would likely be a time in which the planet be either too hot or too cold to sustain life. Okay? The situation is even worse when clusters having many stars. All right, So, good. We got one star. All right, good, good, good. So far, so good. Okay. All right, now the protons and electrons cancel each other out. Good, good. Now we got one sun. We're going around. Good. Okay. What about the orbit of the planet? All right. Our Earth goes around the sun in circular motion. He says, and this is from his text, he's asserting it as a fact, orbital eccentricity, meaning how much the planet deviates from circular motion, is near zero. Okay? So for our planet going around the sun, the deviation is near zero. It's almost perfectly circular. Okay? He continues, if the eccentricity of the Earth's orbit were near 1, okay? So it's zero, near zero, but if it was just near 1, the eccentricity, our oceans would boil when we reached our nearest point to the sun, and freeze over when we reached our farthest point. All right? And he continues, large orbital eccentricities, meaning not close to circular motion, are not conducive to life. So we are fortunate to have a planet for which orbital eccentricity is near zero. All right? I'm sorry, but when we're all through with this, you're not going to become atheists, I don't think, but you're going to be flat down on the ground worshiping the true God Almighty, because it's just unbelievable. So how's he going to get out of this? He wants to. Another fact, another anthropic coincidence. Again, the sun, all right? We're talking about the orbit of the Earth around the sun. Let's talk about the sun itself. Okay. What about the sun's mass? How big it is, our sun's mass. Okay? He continues, the relationship of our sun's mass to our distance from it, okay, that's what he's talking about. The relationship between the mass of the sun and the Earth's distance from it. That's important. Has to be what it is, okay? That is, it's important because a star's mass determines the amount of energy it gives off. The largest stars have a mass, so the largest stars we've identified have a mass about 100 times that of our sun, while the smallest stars we identify are about 100 times less massive. Okay. If we take the Earth and sun's distance as a given, because that doesn't change, right? If our sun were just 20% less or more massive, okay? Coincidence? If our sun were just 20% less or more massive, the Earth would be colder than present-day Mars or hotter than present-day Venus. Okay? Just 20% less or more massive, the Earth would be colder than present-day Mars or hotter than present-day Venus. All right. So, okay. How close are we to the sun? Okay, so here's the sun. Okay. Just right. Okay, and Earth. Okay, sort of wondering how things are going to work out in relationship to the sun. Okay, not so sure yet. Okay, but, okay, we're going to have a zone. Okay, zone, which is actually, in our solar system, very small. Okay, very small. Okay. And scientists call this zone here, right here, around the sun, the Goldilocks zone. Okay, that's what they call it. I mean, this right in the book. Okay. It's the habitable zone. Okay, the habitable zone. The zone where life can exist, all right? And where it's not too hot, not too hot, that's why it's Goldilocks zone. It's not too hot and it's not too cold. It's just right, okay? And, well, here's Goldilocks. All right, so maybe curly. All right, there you go. All right, there's Goldilocks. All right. Good, excellent. Got it again. Okay. Here's what he says. Traditionally, given any star, scientists define the habitable zone as the narrow region around the sun in which temperatures are such that liquid water can exist. Okay? Because no liquid water, no life. Okay? No coffee. Right? No speech. So without liquid water, no life. So the only way you can have liquid water is if your planet is in the Goldilocks zone. Okay? The habitable zone is sometimes called the Goldilocks zone because the requirement that liquid water exist means that, like Goldilocks, the development of intelligent life requires that planetary temperatures be just right. The habitable zone in our universe is, in our solar system, the habitable zone in our solar system, I'm using his own words, is tiny, tiny, tiny. Fortunately, for those who are intelligent life forms, the earth fell within it. Okay? Woo! Excellent. Who would think, really? Okay. Okay, let me just read what he says about Newton. You know, you'd think that, say, Isaac Newton, who saw this and was amazed and said, well, God did it, obviously. He says, Newton believed that our strangely habitable solar system did not arise out of chaos by the mere laws of nature. It is easy to understand why one might think that. Okay? It is, really. Okay, we'll just skip that for now. Okay. What else do you need for life? You need liquid water and you need carbon, right? You need liquid to have life, you and me. You need liquid water and you need carbon. Okay? Okay. Now I'm going to quote, he himself quotes, because carbon's produced by stars, right? And so he's going to quote Fred Hoyle. Who's a very famous physicist, cosmologist, 1950s, 60s, 70s, who wrote this, all right? Because life needs carbon. Hoyle wrote, and he quotes it, "I do not believe that any scientist who examined the evidence would fail to draw the inference that the laws of nuclear physics have been deliberately designed." Whoa. Underline. Highlight. Had been deliberately designed with regard to the consequences they produce inside stars. How do we know all this stuff about nuclear physics and what happens within stars, and how does it relate to the anthropic coincidence? Okay, look at this. So they created computer models that can calculate these forces, and I'm quoting from Hawking himself. Such calculations show that a change of as little as 0.5%, not 5%, 0.5%, a change as little as 0.5% in the strength of a strong nuclear force, or 4%, a change of only 4% in the electric force, would destroy either all carbon or all oxygen in every star, and hence eliminate the possibility of life as we know it. He says this himself: change these rules of our universe just a bit, and the conditions of our existence disappear. Change these rules of our universe just a bit, and the conditions of our universe disappear. Can I give you a little bit more, just a tiny bit more anthropic coincidence? All right? Einstein is famous for saying coincidence is just God trying to remain anonymous. Okay? So he even knew. Okay. Yeah. Okay. Okay. So we have the nuclear forces within a nuclei, and Stephen Hawking continues, if the other nuclear force, not the strong, but the weak force, were much weaker, in the early universe, all the hydrogen in the cosmos would have turned to helium, and hence there would be no stars at all. If it were much stronger, he's giving you the strong stuff here. If it were much stronger, exploding supernovas would not eject their outer envelopes and hence would fail to seed the interstellar space with the heavy elements that planets require to foster life. And he finishes, were it not for a series of startling coincidences in the precise details of physical law, it seems humans and similar life forms would never have come into being. What can we make of these coincidences? Okay. Our universe and its laws, I'm quoting him, I'm not saying this. Well, I'm saying it, but he's saying it. What can we make of these coincidences? Our universe and its laws appear to have a design that both is tailor-made to support us and, if we are to exist, leaves little room for alteration. That is not easily explained and raises the natural question of why it is that way. Okay, and he's even going to show, this is the natural, even before they knew all this, before they could measure the detail of the exact coincidences that allow the universe to be possible, that allow our world to exist, that allow us to exist, man knew this. And Hawking quotes an Egyptian text from 2000 BC. All right? So Hawking quotes an Egyptian text which dates from 2000 BC. And this is what it says. Men, the cattle of God, have been well provided for. He made the sun and earth for their benefits. They could see it then. So, what do we say? Is Stephen Hawking going to draw the conclusion? Let's just think about it for a second. If there is, he says, well, he says, well, can I read that again? That quote, that little thing in the back, that acknowledgement. Just read that again, okay? So where is that? No, where is that? The acknowledgement, okay? Where is that? Do you have it written down? Wait a second, it's got to be right here. Okay. The acknowledgement, well, we'll just try to remember here it is. Acknowledgement. Just think about all the things that he's just presented. Everything, the exact detail. Think about blowing up. If the whole universe blowing up in less than a split second, if everything weren't little electrons and protons, weren't exactly geared toward each other. Think about all that, and then look at this. The universe has a design, and so does a book. But unlike the universe, a book does not appear spontaneously from nothing. A book requires a creator. Just this. Okay, so think about all the things you just heard, Goldilocks zone and all that. And then think of this book. Okay, let's think of an explosion at a paper mill and then connect that to a ink factory, okay? Explosion, and you got, whoops, the grand design. Whoa. Okay, well, I mean, it's possible. All right, it's possible. But then, okay, well, if that's possible, well, then we say, no, I don't think so. It was something else happened there. And then you think of the exact tuning of the universe, just at that level, the level of physics, and it's going to be spontaneous, random, with no intention, no purpose, no mind behind it. And can we just philosophically move a little 2 steps ahead? If it's a mind that created this book, okay, and we pretty much think that it's a mind that designed the universe, right? It's pretty hard to think otherwise. What kind of mind could it be? Could it be our mind? No, we just found ourselves here, right? Could it be his mind? Nah. We still have the universe and he's gone. Whose mind could it be? Well, obviously someone who knew every detail could grasp every detail of every equation, right? And could create things could create things first, make them be, all right? And had control of all the connections, all the relationships, all the mathematical relationships as they develop and until our own time, and then we ourselves. What mind could possibly grasp all that so all those things could go together? Well, that mind we call God. Okay? Okay, how's he going to get out of this one? Because that was just too easy, that conclusion. Okay, how's he going to get out of it? Because he wants to get out of it. Okay?